So how to use that to construct the S matrix for the scattering of magnetic monopoles. And in particular, I will show you how to do the most general 3-point functions. I will tell you how much you can learn about the 2-to-2 scattering of electrically and magnetically charged particles. And have a little bit of discussion of the scattering of gas monopoles. Another interesting story that fascinated people since the 1980s. And then at the very end, if I have time, I will tell you how our results, which is mostly kinematic up here, can actually be understood in some dynamical discussion where the origin of this pairwise helicity that I will be talking about will be the consequence of dressing the states with a cloud of soft photons. All right, very good. So the weird properties of monopoles. So what's so weird about it? So if you take Jackson E&M, probably everybody has taken it. Yes, then one of the nice homework problems is to just calculate the angular momentum that is contained in the electromagnetic field if you have an electrically and a magnetically charged particle sitting some distance r from each other. It's pretty standard. Again, you calculate the Poincare vector, you calculate because that's the momentum density, then you calculate the angular momentum density, integrate it over all of space. So then you find a really weird answer here, yes, which is that the angular momentum in the electromagnetic field for an electric and a magnetic charged particle doesn't depend on the distance of these two objects. Okay? It only depends on the relative position of the electron in the monopole. So this r hat is again the unit vector pointing from the monopole to the charge, and that's what the angular momentum of the field is. And of course, the prefactor is the electric charge times the magnetic charge. Of course, both of them have a Coulomb law for themselves. Yes, one with the electric and the other with the magnetic. So again, this is not by far not a new result. Yes, so this was known by J.J. Thomson in 1904. People are telling me that it was known already, a few decades earlier also. But it's a pretty striking result, as it's telling you that no matter how much you are trying to separate these two objects from each other, yes, the angular momentum in the electromagnetic field is actually not dropping to zero. Yes, it stays essentially constant. Yes, up to this issue of the direction. So depending on how you are orienting them. Okay, so. Of course, if J.J. Thomson knew about quantum mechanics, yes, just from this simple result, he could have read off Dirac quantization, yes, because it's a form of angular momentum, should be quantized. What should be the prefactor? Well, it's E times G. So E times G should be, a half integer essentially. So that could have been, of course, he didn't know about quantum mechanics, so this wasn't the way Dirac quantization was initially introduced, but it could have been in principle. Now, if you have dions, or those are charges those are particles that carry both electric and magnetic charges, then there is a generalization for this expression, where instead of the product E times G, you are going to get this sort of asymmetric product of the electric charge of the first particle times the magnetic of the second particle minus the other way around. Those of you who know about SL2Z symmetry, this is the proper way of forming the product of these charges, the SL2Z variant, that doesn't matter anyway. So if you had dions, then this E times G is always replaced by this QIJ. Okay. And actually, Zwanziger found, the proper relativistic generalization of this expression. Yeah, so this is, just a simple non-relativistic, whatever E&M, and he found actually what the expression of the Lorenz generators corresponding to the electromagnetic field is going to be, depending on the four-vector momenta of the various various particles in the system. And again, he's finding a nice simple relativistic generalization of that. with the prefactor as expected being this Qij. Yes, and there's a little bit of a subtlety here. You get this plus minus sign, and that's of course related to the fact that you're trying to express this in terms of the 4-vector momenta of the various particles, but you see the actual result depends on the direction. Yes, so this is really an asymptotic expression depending on whether you go asymptotically large time or asymptotically early times. Yes, then of course the directions can be approximated by the momenta or by the relative momenta of the various particles, but depending on whether you go into the future or in the past, you're going to get a different sign for this. Okay, so that's why this plus or minus sign, yes. And again, this is kind of important because it's telling you that this expression will be differing by a sign for the in and the out fields eventually. Okay, very good. So this very simple consideration tells you, some of the basic weirdness of the magnetic monopoles, namely that the conserved angular momentum of the system is different from that of the field-free period. Yes, so the conserved angular momentum, when you have magnetic monopoles present, is not going to be the same as the angular momentum of the free period. The asymptotic states will not factorize into one particle states, yes, because I'm trying to separate these two states from each other, yes, but the angular momentum is still going to be remembering that there was a product of an electric and a magnetic charge in the system, yes, and there also will be no crossing symmetry for the S matrix, which you can understand because the crossing symmetry will tell you that you can move sort of a magnetic monopole from the future to the past, yes, but monopole, anti-monopole will not have this additional angular momentum contribution, yes, so clearly, the system is not quite equivalent. All right, just another way of seeing, this weirdness. You can see this also from a quantum mechanical approach to magnetic monopoles. Yes, so you know how to write the Hamiltonian of a charged particle in an electromagnetic field. Yes, and then you can just ask, okay, so let me just take the vector potential for the magnetic monopole. That's something that has been known for a long time. Wu and Yang and all those people have told you what the vector potential for the magnetic monopole is, and then you can try to ask the question, okay, so if I now put in the magnetic monopole here, what will be the expression of the conserved angular momentum? Yes, so the naive expression would be to just take, R cross the covariant derivative. Yes, but you can just ask, what kind of commutation relation does it satisfy, and it doesn't give you the usual angular momentum commutation relation. And you understand from the previous answer why, yes, because there is another piece there, yes. So in fact, if you augment now your naive expression with exactly the same expression as we have just, learned from this simple Jackson calculation, the quantum mechanical equivalent of that, yes, then that indeed is going to now satisfy the angular momentum commutation relations. Okay, so again, in non-relativistic quantum mechanics, we will have the same answer as what we had before. So again, this is all to tell you that there's something going on here, yes, with the system of electrically and magnetically charged particles. And one of the things that we see is that the two particle states are not really factorizing into the one particle state. So the question that we have been trying to understand is, how does this show up when you're looking at the representations of the Poincare group? How does this extra effect actually manifest itself? Okay. Yes.
Actually, if E and G satisfy saturated Dirac quantization,
right. So I'm assuming that
that's the lowest thing. Then does that give you spin half?
Right, spin half.
So you take two bosons and you get a fermion.
Two bosons and you take a fermion. You get a fermion. Absolutely, yes. Very weird. Yes. Okay, so the story that we have here is I would like to first just remind you how Wigner showed what the representations of the one particle states are, and then from there I would like to tell you what the subtlety is when you have multi-particle states and how that can show up in the representations of the Poincare. Okay, so this is something that in principle, it's taught in QFT classes, but not every QFT class actually teaches it. So let me give you just a very quick reminder, how you do the representation. So this is again something from the 1930s by Wigner. So what he says is, okay, let's start with the momentum eigenstates, yes, because p squared is a Casimir operator. So p squared is going to be fixed in a given representation. So that will be one of the things that is going to characterize the representation. So that's what we call the mass squared. And for every fixed mass squared, yes, you can actually choose a so-called reference momentum. Yes? So what the reference momentum means is essentially go into the simplest frame, go into the frame where the system has the biggest symmetry. So if you have a massive particle, you can always go to the rest frame of the particle. And so that's what will be the reference momentum for a massive particle. And for a massless particle, you can of course not go to the rest frame, but you can rotate the momentum in the z direction. So that's what we call the reference momentum for a massless particle. Okay, and then an arbitrary momentum that is satisfying the mass shell condition, yes, actually can be thought of as the boost of this reference momentum. Okay, so any p that is satisfying p squared equals m squared, so can be written as a Lorenz boost acting on just the basic reference. Okay. Now here is the trick, Wigner's trick. Yes. If you take the combination of these three transformations, so do an arbitrary Lorenz boost, then take the general Lorenz transformation, and then do the inverse of that boost. Yes, this is actually going to leave the reference momentum unchanged. Okay. Why? Because if I just act with this combined transformation on k, LP on k is p, lambda times p is lambda p, and then L inverse of lambda p is going to take lambda p back to k. That's what the definition of L holds. Okay, so these transformations, yes, they leave k unchanged, so they are corresponding to the symmetry group of the reference momentum. Okay, so this is what we call the little group of this particular particle. Okay, and so if this is true, yes, then the corresponding representations, yes, in the Hilbert space for this particle must actually be rendering a representation of the little group itself, yes, on the reference state. Yes, so if I now take the state corresponding, the quantum state that is corresponding to this reference momentum, yes, and here this k sigma is just the k is telling that this is a state corresponding to the reference momentum. And the sigma are all the other quantum numbers. At this moment, we don't quite know what all these other quantum numbers are. Yes. Then acting with this combination of transformations on the reference momentum. Yes. Because the reference momentum remains unchanged. Yes. All it can do is it can act on these other quantum numbers, and it has to act with the representation of the symmetry group of this reference momentum. Okay, so this D is going to be a representation of the little group. And so this is how SO3 is showing up for. This is how spin is actually coming out of group theory. Yes, this is why you're looking for the particle-like representations of the Poincare group, and you're going to get an SU2, yes, which is the cover, yes, of the SO3. Yes, so this is how spin is showing up. This is how spin is introduced in particle physics. Okay, now for massless particles, there is a little subtlety. It turns out that the little group, if you strictly speaking calculate what the little group of that reference momentum K00, E00E is, it's actually what is called E2, is a two-dimensional Euclidean group. So it's not just SO2. It contains rotations and translations in a two-dimensional plane. That's why it's called E2. It's the transformation of the two-dimensional plane. So if you look at the representations of this E2, that actually itself is something relatively complicated. But it turns out that, a large set of those representations contains a continuous parameter, sort of a continuous generalization of spin. Okay, so it turns out such a thing could, in principle, just based on good theory exist, but we don't have any physical, any good physical implementation for those. So in practice, we usually just ignore that. Yes? Again, it doesn't mean that there will never be a system where those are useful, but we don't know about it. So we usually just make our life easier and say that instead of looking at representations of the full Euclidean group, we usually just look at the subgroup which is corresponding to the SO2 rotations, the rotations around the z-axis, which is kind of obvious when you look at the fact that the momentum of the massless particle is going to pick a preferred direction, and then the rotation around that is a one-dimensional rotation, an SO2 or U1, and that's what we call helicity. Okay, so that's how helicity shows up in particle physics, and that's how helicity is different from spin in massless versus massless particles. Okay, so then you can go ahead and find now the full set of representations of any, not just the particle corresponding to the reference momentum, but to an arbitrary momentum. And again, the way it's done is that you have to now use this representation corresponding to this combined transformation. Yes, so this combined transformation is, again, essentially telling you, let's go first into what this W does is it tells you, go first into the reference frame, into the reference momentum, the rest frame of the particle, yes. Then do the rotation in that frame and then go back. Yes? So this is what the general Lorenz transformation of a state is, that you have to take the representation of the rotation group corresponding to this combined element, which is containing, going to the rest frame, doing the rotation there, and coming back from the rest frame. Right? So this is what the representations of for a particle are, and this is again Wigner's construction for particles. And again, what this is saying, even though the formula may look complicated, it's just telling you, go and find the frame with the biggest symmetry. Find the frame with the biggest symmetry, and then find the representations corresponding to that symmetry, that possible biggest symmetry, and then any Lorenz transformation, the effect of any Lorenz transformation, you can make up by these composite things. So you first go to that frame, then you do the general rotation, and then go back to your original. Very good. So that's, again, it's old story, 1930s physics. Still fun to remind ourselves every now and then, but nothing new here. Okay, so what about multi-particle states? Okay, so usual assumption is that, when you have two particles, you can just take the Dirac product of the particles, and those give you another representation of the Poincare group. Fine, And of course, nobody says that they don't. Yes, they do give a representation of the Poincare group. But it's not quite clear, yes, so what I will try to argue that there could be something more general than that. And that's the one that is actually going to be relevant for the case when you have magnetic monopole present in the. Okay, so here is our hero for today, Daniel Sanziger. So he was actually thinking about this question in the 1970s. And he already noticed sort of the essence of what I'm going to be talking about, which when you have two particles, okay, in particular, we are going to be talking about the monopole and the charge, but for now, it's generically two particles. there's actually another special frame. Okay. And that's the center of momentum frame for these two particles. Yes, when you have two particles, there exists always a frame where the momenta for these two particles is actually back to back. Okay. And in that frame, that system of these two particles has an additional symmetry, yes, which is just the rotation around that momentum for the two particles that are pointing back to back for each other. Okay. So there could be another symmetry transformation for a pair of particles, yes, which would not be captured in any way by just considering the little groups for the individual particles. Okay. So you know what Zwanziger did and what I'm showing you is that you can go ahead and repeat the whole story of Wigner for two particles, and for simplicity, I'm just going to pick two particles without spins. So I'm assuming that their initial little groups are just trivial. That's the representations that I choose for their own little groups is trivial, yes. And yet I can do the same story still, you know, I can define now a reference momentum for the pair of the particles. We'll choose this to be the center of momentum frame, yes. So the momenta in this frame are going to point back to back. The energies are not equal, yes. These are not massless particles, you know, they are massive particles. They're just two general massive particles, yes. And yet I can always go into this frame. You can calculate, you know, what the specific momentum in this in the center of momentum frame is. Yeah. So this is a Lorenz invariant quantity. Yes. Why is Lorenz invariant? But it is a special frame. Yes. So from wherever you go, yes, it's always the momentum in that special frame. So this is a Lorenz invariant object, even though it looks weird. Yes, but because it's the momentum in a given frame, you know, it is something that is Lorenz invariant, and from any frame you can calculate it, yes. And the energies of the in this particular frame, yes. Now then you can again, you know, just continue the story. Now I have this reference momenta, and then I can get any pair of momenta by boosting this reference pair, yes. And the boost here, this is the same boost, yes, of course. This is the same boost. That's what is special about this, that you know, there is a frame where they are back to back, means that, you know, from this reference pair of momenta, you can get an arbitrary pair of momenta for these two particles. Okay. So what we are saying is that in this center of momentum frame, there is an additional remaining symmetry. There's an additional rotation around the z-axis, a U1 symmetry, yes, which you can perform. So there's an additional symmetry. So there's an additional little group here, but it's a little group that is characterizing the pair of particles. It's not characterizing any of the individual particles. It's characterizing the relative sort of, you know, transformations of these two particles. Yes. So this is what we call the pairwise little group, and this is the thing that was, for me at least, very confusing, and that's why, you know, with John and Yuri for a long time, you know, we sort of understood it. We read the paper of Zwanziger, but, you know, he doesn't say very clearly. So I think, you know, technically he understood everything, but I'm not sure that the physics was completely clear. Yes, but there is another little group here. Yes. There is another little group that is independent and in addition to the one particle little groups for each particle. Because whenever you have a pair of particles, what you have to do is you have to define what the representation for each individual little group is for the two particles. And in addition, you have to assign a representation to this pairwise little group. Yes, it's pretty clear in this spinless case, yes, because I assume that there is no individual little groups, I mean, that they are represented trivially, yes, yet I can choose now still a representation for a rotation. Yes, and this rotation is not any of the little groups of these. Yes, it's referring to a completely different frame. It's a different choice, and you can choose this independently from the spins or helicities of the single particles. Okay. So again, so the point is that that you have to choose now a quantum number under this U1. Yes, so we call this, because it's a U1 group, yes, this pairwise little group is actually going to be a helicity-like quantum number. So I'm going to call this the pairwise helicity for the system. Yes, and then the general Lorenz transformation for the system will be just given by one of these additional phases, this helicity transformation. So you can go ahead and do all of the story. Yes. So again, of course, in the special frame, it is just going to be a rotation around the z-axis. In the general frame, it's not a rotation around the z-axis, but you have to just do Wigner's trick, that you first go into the frame where they are back to back, then you do a rotation, and then then you go back to your original frame. Okay, so the overall effect will be a phase, an additional phase. Right? So this is what we call the pairwise helicity for the system. And again, it's this, it's a phase, but it's easy to write a phase, yes, but this phase is corresponding to this composite set of transformations that I have outlined for you. What is the physical meaning of this? Yes, in the special frame, yes, in the center of momentum frame, it's clear that this phase will give you an additional contribution to the z component of the angular momentum of the system, telling you that this system has an additional angular momentum, even though the individual particles don't have any spin. Okay. So, in particular, what we are saying is that if I'm trying to now identify, these two particles as an electrically and a magnetically charged particle, yes, then I should actually identify my choice for the pairwise helicity, yes, with this product of the electric and magnetic charges for the charge and the monopole. Okay, so this is what is beautiful about this, yes, that of course, until here this was just group theory. Yes, we said that a two-particle representation doesn't necessarily have to be just a direct product of the one-particle representations. There is a possibility here for an additional quantum number, yes, but it could have turned out that it's just some nice math that doesn't have any physical consequences. Yes? Just like, for example, as far as we know now, yes, the fact that the middle group for a massless particle is E2 and not SO2 doesn't have any physical consequences, in the sense that I don't know of any reasonable physical system that is actually calling for those more weird representations. Now, the beauty of this additional quantum number is that I know a system that is actually calling for you not have zero pairwise helicity, yes, and that's exactly the charge-monopole system.
And the fact that this new quantum number goes along this axis is the same as the fact that in your non-relativistic model you had R.
Exactly. Yes. Exactly. That's the origin. And of course, in the general frame, yes, you have to do this more complicated composite set of transformations. But it's complicated, but it's there. You can calculate it, and later on, I'm actually going to show you how it exactly acts. Okay. So a few comments. At least for massive particles, this pairwise little group is really SO2. Doesn't have the subtlety of E2. I checked. There are no other generators of the Lorenz group that are preserved. So that's the case. And it's SO2 for massive particles. Yes. So there's nothing. You get this helicity type quantum number, even though neither the electron nor the monopole is actually a massless particle. So of course, what will be massless is, there's the electromagnetic field and there are photons there, and so it's not super shocking.
So the common group of SO2 is R. So at this level, we would have had arbitrary. But we only get spin half.
Right.
Presumably, we only get spin half. Is there a group theory?
Well, is there a group theory understanding? I don't. Okay, so.
Oh, is there?
I'm just.
But yeah, I suppose. I see.
All right, very good. And so again, so it's a true U1 helicity type phase for massive particles. Now another comment is that for higher little groups, so now you may ask, okay, so I told you there's a pairwise little group. Is there now a quadruple little group? Yes. Should we worry about all of those? Yes. Well, actually, the answer is no. That there isn't any. Yes, and the reason is that when you try to add up zero momentum out of two momenta, yes, then they are going to be back to back. Yes, but if you try to add up zero momentum out of three momenta, yes, then there's no more symmetry left in that system. If in terms of maybe that one is more easily seen if you try to say that if you use up some of your symmetry your rotational symmetries to put one particle into its own rest frame, then the momentum of the second particle would pick a direction, yes. But if you have a third particle, then there's no more symmetry left over. Okay, so there's no such a thing as a three or in 4 dimensions. Yes, if you go to higher dimensions, yes, then there would be such an object. Now, I don't really know if that actually has any relevance. The one thing that we have figured out is that if you're looking, instead of particles, you can look at brains, and there is sort of an analog of the Dirac quantization condition for brain-like objects and their magnetic duals. And so actually, this pairwise helicity can be generalized to p brains, and then their magnetic duals, which I forgot, are like d minus p minus 4 or something like that. High brains. Okay, so there is such a concept for brains, and that's the one generalization that we know that could be physical. The rest, again, the group theory is there. You can look at particles in 5 dimensions. There could be 3. I don't know any implementation of that. Okay. That's all. Okay, now how about the case of particles with spin? The general case, well, it's not too shocking. Yes, so if you now have n particles instead of just 2 particles, the most general situation that we can imagine here, and we actually gave a construction for this. I'm not going to repeat it because it's kind of boring, but it was important for us at least to see that you can really build that up. And what you do is that you pick a 1 particle little group for each particle, and then for each pair, in addition, you're going to pick a pairwise helicity, and then the most general transformation of these n particle states built up of this form will be, there will be the matrices for each of the 1 particle little group, and then there will be phases for each pair of those particles. So, and again, with the charge-monopole system, you would assume that each, if they are sort of mutually non-local with respect to each other, any pair, then you would assign a pairwise helicity. If they are not, then you would assign to it. Okay, you can give some discussion in terms of guts, but it's all right, very good. So we have this concept. Now, how should we actually take advantage of this in terms of the scattering of trying to describe the scattering of electric and magnetically charged particles? Well, what we want to do is we would like, so what we have learned in the last decade or 2 or whenever. Of course, some people knew it earlier. I didn't, we were brought up by Nima to change our viewpoint of how to discuss scattering amplitudes. Yes, so we are trying to see, how to implement the fact that there is a new little group into, actually building up the scattering amplitudes. Okay, so just a quick reminder for those of you who, like me, who took field theory before, these spinor-helicity variables were very commonly used. What people usually do is, yes, they are introducing these so-called spinor-helicity variables as the basic building blocks for the S matrix elements or the scattering amplitudes. And the way they are defined, again, so these are spinors, yeah, so So these are spinor-helicity variables, spinors in the sense that they carry a spinor index. That's a normal, whatever, various spinors, but either an undotted or a dotted spinor, depending. So that's what it means, whether it's square or an angle bracket. Yes, and the main property of the spinor is that under a Lorenz transformation, it actually picks up exactly the right little group phase if it's a massless particle. Yes, this would be the little group helicity. If it's a massless particle. If it's a massive particle, yes, then it's going to have another spin quantum number. Yes, so this is a spinor quantum number. So this is a Lorenz quantum number here, the alpha, and this I is the quantum number under the little group. Yes, so that's what the general spinor-helicity variable is. Yes, so under Lorenz transformation, yes, it's going to pick up the transformation under the little group. Okay, very good. And so then, essentially, writing down scattering amplitudes is just equivalent to asking, what are the right contractions of these spinors such that they end up carrying no spinorial indices, yes, because the S matrix or the scattering amplitude, it doesn't carry Lorenz indices, but it carries, transformations under the little group. Yes. Yes.
So it's now it's not guaranteed. Is it that it's not guaranteed anymore that there's like a local QFT kind of?
Yeah. So here I'm giving up. This is the Nemes approach. Yes. That let me just take the states, and of course that's what the beauty is of this formalism for magnetic monopoles. Yes, because there you are struggling with writing down a nice QFT formulation. Yes. I mean, there are some, and I will tell you what people usually use, but it's not Lorenz invariant. So anyway, so that's the whole beauty of this formulation here. Yes, Nima always says, I could have calculated these amplitudes even if I didn't have a Lagrangian. Yes, and now we are saying we have a situation where we actually don't have a Lagrangian. Yes, which is the scattering of electric and magnetic charges. Yet this formalism, at least up to a point, and I will show you, it's not going to give you everything, yes, because at some point some dynamics needs to go in, yes, and we are essentially giving you, kinematics here. Yes, but there are additional kinematic constraints here, and I'm going to show you how far you can push this in terms of generating the scattering. Yes, but for now, yes, for these objects, yeah, for this you didn't need a Lagrangian. Yes, this is like the amplitudology. Yes, if it's massless, then you get these spinor-helicity variables, and if it's massive, then you call them bolded spinor-helicity variables, which are really not helicity, as it has as your two column numbers. So this is the Lorenz index, and again, the story of writing down the scattering amplitudes reduces to, contract all the Lorenz indices, the spinor indices such that it carries the right quantum numbers under the little group, because the S matrix, yes, so there you have some incoming external particles, they carry little group quantum numbers, yes, and so you are trying to mimic that. So that's the whole story, yes. So again, what I'm trying, the upshot is that without magnetic monopoles, yes, we have these basic building blocks, these spinor-helicity variables, which we know how they transform under the little group and at the Lorenz group, yes. And now, when we have an additional little group, as this pairwise little group, we have to find sort of the generalizations of what are the objects that are going to carry the pairwise helicity. Okay? And in fact, one of the problems with writing down scattering amplitudes for magnetic monopoles is that, in fact, they do pick up an extra phase, and without this additional ingredient, you would never get the right answer. You would not get the object that has the right transformation properties, because you would be missing that phase. Okay, so that's what we did. So we went ahead and sort of constructed the analogs of these spinor-helicity variables for the pairwise helicity. So we call these the pairwise spinor-helicity variables. Now, since these are some U1 transformations, we expect to be corresponding to some sort of a massless momentum, yes? But it's not, none of the particles are massless here. However, out of a pair of particles, pair of massive momenta, you can always make a linear combination that is actually sort of like a massless moment. So if you have P1 and P2, neither of them is massless. So you can take a linear combination of the two and make it a massless moment. Okay? So in fact, that's what we did. And so we call these the flat momenta. And the reason for this weird notation is because in the amplitudology, actually, this problem of finding the corresponding massless momentum for two non-massless states is something that showed up before, because when they were trying to do loop integrals, it turned out that it was much easier for them to do the loop integrals when you have massless states. So and they denoted it with this flat symbol. So that's why we try to keep to that. So okay, so in the special frame, in the center of momentum frame, it's actually very easy to guess, what this flat momentum is going to be. Yes, it's going to be, a momentum that is pointing in the direction of what the momenta are, but it should just be massless. So it should just be, 1, 0, 0, minus 1. Okay, and then you can go into any other frame and by boosting, yes, you can get these pairwise spinor-helicity, this pairwise flat momenta, yes, another frame, and you can show that indeed these are just going to be the linear combinations of the one and the other momentum, yes. So these are just, so these things here are, these are the center of momentum quantities for the energy and the momentum of each of the, so those are Lorenz invariant quantities, yes. So for a given system, that those are fixed, yes. And so you can see that these are indeed just going to be linear combinations of the two momenta, like we guessed, yes. And here I just have the explicit expression for what the right things are, yes. And so now we have these massless momenta, yes. So now we should just go ahead and, really just do the same thing, just pretend that these are momenta and get the corresponding spinor-helicity variables, just like as if they were momenta of ordinary particles. And those will be, by definition, essentially, by definition, those are going to be the spinor-helicity variables for the pairwise helicity. Okay, and then those are the things that you will have to add on. You will have to keep using when you're trying to make the scattering amplitudes for electrically and magnetically charged particles at the same time. Okay, so again, so you can go ahead and find what the pairwise helicity variables are for the special frame, for the center of momentum frame. So here just 1, 0, and 0, 1. And then, of course, you can go ahead and boost it into into any other frame. And again, by construction, these pairwise spinor-helicity variables, yes, they are exactly going to be picking up that phase. That's how we constructed it. Yes, that they are exactly going to be picking up that phase that is sort of missing from the Lorenz transformation of the system. So what we are saying is that when you have an electric and a magnetically charged particle present at the same time, you will have to use, depending on how much angular momentum is contained in the electromagnetic field, you will have to use a bunch of these pairwise spinor-helicity variables when you're constructing your scattering amplitude in order to make sure that your S matrix actually does have the right Lorenz transformation properties. Without it, it will not have the right Lorenz transformation properties. So you will have to use a bunch of these, and the rules are pretty simple. Right? So the rules are, so there's this additional column number here, and these guys, they are just going to be under the little group. They will only pick up a phase under the pairwise helicity. That's how they were designed. Yes. And then you have still the ordinary spinor-helicity variables. So those will take care of the ordinary little group transformation properties of the S matrix. Yes. So yes.
So you're in the end keeping track of the angular momentum of the field.
Exactly. That's what. Yeah.
So with this, often we, I mean, in less fancy formalisms, we expand an S matrix in spherical harmonics.
Right.
If you just change that expansion to monopole spherical harmonics,
Right.
that will account for all this.
So we will show actually that the monopole spherical harmonics are actually just products of these. Okay. And it's, so that's something exactly that was known. So the eye actually pops out from this formalism pretty naturally. And so we did that story. I don't know how far I'm going to get into that, but we did the story of doing the decomposition into angular into the partial wave decomposition, yes. And then actually the product of these I mean, these are specific functions essentially, and they are going to be exactly the monopole spherical harmonics. So if you didn't know about them, you would discover them right here. Okay.
Yes. So I to follow through on the formalism that you talked about,
Yes.
the pairwise physics. But I missed the argument is why this is appropriate for your monopole system.
Well, so what we are saying is that the monopole system, because there's this additional angular momentum, yes, is going to have an additional phase, yes. When you take a monopole and the particle and you try to write down what the possible scattering amplitude is in their Lorenz transformation, so there will be an additional phase popping up. Okay, and what I try to do with this quantity here, I now constructed just out of the momenta of the system, yes, another quantity that transforms exactly, that gives you, that exactly saturates that phase. And what I'm telling you is that in order to now give you a properly Lorenz transforming object, you will have to use a bunch of these also, yes, in order to sort of, get sort of a candidate scattering amplitude. Yes. That's how amplitudology works. Yes, that you know how the S matrix transforms, and you just make up objects that have that transformation property. Yes.
Sorry, I didn't understand this how when it was important that the particles were charged. But your argument was for generally this Lorenz transformation and so on. I didn't see where it started.
Right. So the group theory argument, the initial, didn't say anything about charges. Yes. So what we just said is that there's a general quantum number Q. Yes. And then the question is, how do you choose Q? Yes. For any pair. Yes. And what I was arguing is that at the point when I'm actually trying to choose the Q for a pair of particles, yes, I want to identify that with the product of the electric and the magnetic charge. But the group theory absolutely doesn't tell you that. It just tells you this is a possibility. There's another possible quantum number there. Yes, but I could just choose all of them to be zero. And in most cases, in fact, you should choose them to be zero. Yes, because the system factorizes. You move them apart, and they will behave like single particles. They don't know anything about each other. Yes. So it's really just a product of two single particle states, and when that happens, then you should choose Q to be zero. Yes? What I was trying to argue, maybe I didn't spell it out, I shouldn't have spelled it out to this level, that when I have an electric and a magnetic charge, then the system, I was arguing at the beginning, really does not factorize. Yes, but there is this additional angular momentum there. We know what the effect of that angular momentum is. It's exactly the same as this. So I'm going to make this identification that Qij is going to be EI times Gj minus EJ times Gi. Okay, so again, that's how I'm implementing the representations of the particle. That I will choose a non-trivial pairwise helicity quantum number whenever I see that I have these non-local charges.
So the group theory itself, there was nothing to tell you.
The group theory did not tell you.
Zero when the.
Yes, the group theory just told you that this column number could possibly be there. Yes. Take, and then what we're saying, okay, but we are not mathematicians, we are physicists. Yes. We want to now apply this to, any given, particular implementation. Yes. And for that, I'm gonna, make this identification. And that's what I was saying, that I'm actually happy that, it wasn't just an empty group theory in the sense that could be non-zero, but why? Yes, that we have a why that it's non-zero. Yes, because we have this particular situation. Yes,
So in this monopole description, you have some electromagnetic field run into the past, but this is not. So in your S matrix, this is not. You just have the fact that there is an electromagnetic field in the photon.
The electromagnetic field of the charges. Yes.
Yes. But when you're doing the S matrix, you're just taking a pair of. And the fact that there is.
I'm just taking a pair. I'm just taking a pair, and so that's something that I'm not sure I will get to that, but so then we try to understand. So what is the dynamics of this whole? Yes. But it turns out that it is actually really picking out the very soft components of the electromagnetic. It's really the soft photons that are going to be dressing the states, and it turns out that. It turns out that sort of the usual Fock space states that you start out with, due to these soft photons, are actually not the right asymptotic states that you want to be using, but they will be the so-called dressed states. Okay, so I'm gonna, probably I will have to, rush over that, but for those of you who are interested, I can stay and explain. All right, very good. So again, so then if you want to write down a scattering amplitude, like let's say the simplest thing, just as a stupid example, let's say that there is a massive fermion that decays to massive fermion plus a mass scalar, and let's say that the particle that decays is a dion, and it decays now to an electric charge and a magnetic charge. So the initial one carried both electric and magnetic charges, and now it decayed to one that only carries electric charge, and the other one only carries magnetic charge. So the Q in the final state is non-zero. Yes, and we just assume that it's -1. So -1 is twice the minimum amount of Q. So that means that you will have to use two sets of these pairwise helicity variables. Yes, so you will have to use two of these flat variables. Yes, and then in addition, we have a fermion, so that with the spin 1/2. So we have to use one spinor-helicity variable for the initial state and one ordinary spinor-helicity variable for the final spin 1/2 state. Yes, so this is how how you're going to make up an amplitude now that has the right transformation properties. Okay, so you can check that this one has exactly the right transformation properties. And in fact, other combinations that we can try to write, they will be equivalent to this one by the Dirac equation. Okay, now for the 3 point, actually you can write pretty nice general expressions for how to get the right number of contractions. So if you say that, okay, so this is the part that is corresponding to the original to the ordinary one particle little groups. Yes, so you have if you have particle with spin 1 became the particle with spin 2 and particle with spin 3. Yes, then you have to use 2s1 ordinary spinor-helicity variable. So it will have 2s1 spinor indices. Yes, and then the same for the decay products. So in total, you have S1 plus S2 plus S3 spinors times 2. Yes, and so you need to match, these spinor indices with the spinor indices from the pairwise helicity variables. And but you also know that the pairwise helicity has to add up to Q23, yes, because we know what the common number under Q23 has to be. Yes, so then the plus and the minus types, yes. So we know the sum has to be exactly 2s hat, yes. That's the number of these pairwise spinor-helicity variables that we have to use in order to saturate all of these spinor indices. And then, one of them, the minus, you'll have here minus q, and the other have you'll have plus q. So this is the number that we have to use. Yes. So this will actually give you a selection rule. Yes, it's going to tell you that the pairwise spinor-helicity of the final state cannot be too big. Yes, if it's very big, if it's bigger than the sum of the spin of each of the decay, the mother and the daughter particles, then actually there's no possible amplitude that you can write down. Okay, so you will get a nice selection rule here, yes, and for q equals 0, you will recover the usual expressions that was written in Nina's paper about how to construct the general scattering amplitudes for ordinary particles. Okay, so again, for decays, for 1 to 2, you can essentially fix everything. Okay. Now here comes the story about the 2 to 2 scattering. Yes, so that's of course much more complicated. Yes, so the kinematics will not fully fix the S matrix. Okay, some dynamical input will be needed, but then of course we can try to go the route that Shiraz was asking. So we can do a partial wave decomposition. Okay. And we will actually see that the kinematics fixes almost everything up to some phase shifts, like in quantum mechanics. Yes. And those phase shifts, again, those are dynamical things that we don't really know how to calculate, except for the lowest partial wave. So it turns out that one, because there will be only one possible amplitude that you can write down for the lowest partial wave. So that one is going to be completely fixed by unitarity. And that is the one that will give the famous helicity flip. So this is something that, C and Yang and his collaborators, Callan and Goldhaber, were studying in the 1970s. So they figured this out, already just based on non-relativistic quantum mechanics. They did this partial wave decomposition. They were the ones who found those monopole spherical harmonics. So the higher partial waves will be in these monopole spherical harmonics, and they appear naturally as expected again, by C and Yang back to 75 or something like that. So again, I'm not going to show all of this because I'm running out of time. That's one, and the other is there's a little bit of more heavy formalism, so it's not that super exciting. But again, what we did is so just a year or two before us, people discussed how to do the partial wave expansion in this amplitude formalism. So that's something that Jing Shu and his collaborator showed. So we just showed how to generalize that if you also have these pairwise spinor-helicity variables present in the system. So that's how you get your Lorenz generators. And then there is sort of a version of the Wigner-Eckhart theorem that is showing up here. So you can find out, how to write, the various quantities that are characterizing the external states and what their spin is going to be. Again, I'm not going to discuss this very much here. There will be parts of it that are completely fixed by group theory. So those are like the Clatz-Gordon coefficients in the Wigner-Eckhart theorem, and then there's some dynamical input that is going to be needed. So we did this. We applied this to the scattering of an electric charge on a magnetic monopole, and we went through all the possible allowed states. We found exactly like predicted by C and Yang that for the lowest partial wave mode, there's only one amplitude, and again, they are basically just consequences of that one very simple, stupid selection rule that I showed you for the 3-point function. So we calculated that. So the lowest scattering amplitude we could fix completely, we could reproduce the helicity flip that is showing up there. And for the higher partial waves, we were able to identify again, just like we discussed there, that actually, these so-called monopole spherical harmonics are actually going to be showing up here. And again, they are just going to be related. So they are these D matrix elements, yes. And these D matrix elements, as you can see here, are actually nothing but just the direct products of these pairwise spinor-helicity derivatives. So they are actually showing up very natural in this case. Okay, and again, we were able to sort of then do a general result in the massless limit, and if there was a phase that we couldn't fix here, and that's essentially the phase shift. So that's the dynamical information that our formalism at this point is not able to fix. Of course, Kazama calculated it in his particular non-relativistic limit, so we could cheat and try to take his, and then of course really have it. It's a little bit of a cheating, because really you need at some point some dynamical information. All right, very good. Now let me say just a few words about gut monopoles and gut scattering. Yes, so that's of course a very important and interesting physical problem. Yes, just to remind you, that's something that lots of people, including me, have been confused for a long time. How to think about the gut monopole. Yes, so I'm talking about the SU5 here that's broken to SU3 plus SU2 plus U1. Yes, and then there's the usual tooth polyatomic monopole, which you get from SU2 broken to U1. Now the key here is to understand where is the SU2. Yes, where is the SU2 of the tooth polyatomic? Yes, well, there should be an SU2 that is broken to U1. Yes, so if you arrange the web such that this upper part is the SU3 and this lower part is the SU2, yes, then the SU2 that gives you the monopole is going to be sitting here in the intersection, because that's the one that is broken down by the web to U1. Yes, so this SU2 is a weird beast. Yes, it's the one that that is hanging in both into SU3 and SU2. So if you are trying to find what the matter content of the standard model is under the SU2 that is giving rise to the monopole, yes, you get this weird stuff, yes, because I mean you are asking, how do the representations, the 10 plus 5 bar of SU5 decompose under just an SU2? Yes, so well, all you can get is doublets or singlets. Yes, so actually the standard model matter field under the SU2 that is relevant for monopoles, yes, is going to be just a bunch of doublets, but they are not your usual doublets. Yes, they are weird things. It contains an electron and then a conjugate B quark. Yes, because again this SU2 is the one that is hanging into partly the SU3 and partly the SU2. Okay, and so this is so these are the four doublets, and from the point of view of the SU2 of the monopole, yes, these four doublets are completely equivalent. And so that's why you will have an SU4 horizontal symmetry here, yes, because from the point of view of SU2, this is just a theory with four doublets for the SU2 monopoles. Yes? So that has an SU4 global symmetry. Yes? Of course, it's not identical under they are not identical under the gauging of the SU5, how it's embedded. But if you just look at the monopole dynamics, these things are identical. Yes? And then, of course, you can ask the question, so now how do you describe in our formalism the scattering of, for example, a proton on a magnetic monopole? And so this is the very famous Rubakov-Callan process. Unfortunately, Rubakov just died, and he was really a giant of the field. So I'm very, very sad about his passing a few months ago. Anyways, so so this is essentially the scattering of the proton on the monopole. So you take here the two of the quarks out of the proton, and here we are focusing on the S wave incoming state such that both of these can reach the core of the monopole. then you can go ahead and write the incoming part of the amplitude, yes, because you're trying to generate an S wave, a zero total angular momentum out of the first quark and the monopole. So you're going to use one of these pairwise spinor-helicity variables for the first guy, also for the second guy. Yes. So that's all good. Now the question is, what is the outgoing state? Yes. In principle, if you are naive, it could be the same if there's forward scattering. Yes, but if you then ask what is the corresponding scattering amplitude, we discussed that you need to have a helicity flip for the lowest states. Yes, so actually the forward scattering is actually not allowed, and that's something that if you just brute force in our formalism try to write down the scattering amplitude for forward scattering, you will find that it's in fact zero. Yes, that's very good. So in that sense, we would find the Rubakov-Callan effect in our formalism as predicted. And you can find also, using the quantum numbers that you have, what the possible final state, the helicity flipping final state in our system is. And in this case, all the gauge quantum numbers are going to be preserved. Of course, the global quantum numbers, like baryon number, will not be preserved. So you will get this very famous expression for the Rubakov-Callan scattering amplitude, where you scatter a proton on a magnetic monopole, and you get a baryon number violating process. Okay, and because again, this is the only amplitude that is allowed, etc. is unitarity bound, so you can actually even calculate, or estimate the coefficient of it, and it's going to be given by lambda cube speed. So this is a very large baryon number violating cross section. Okay, so we could say this is sort of an on-shelf way of seeing, the Rubakov-Callan. Now, there's another puzzle here that has bewildered physicists for a while. So you can also scatter, instead of a proton, you can scatter a positron on the magnetic monopole, and you have exactly the same kind of story that you try to find what the initial state is, and then you try to find what the possible final state is. And it turns out that for the only possible final state that you can come up with, that scattering amplitude also vanishes. Okay, so that's something that has, people has up in arms, there's no allowed final state. People are trying to do, truncate this to a two-dimensional system and find, what the, anyway, I just want to make the long story short, at least for our case, if we use our variables, what we were able to identify is that there is actually a variation of the final state that that seemed to go to zero. Yes, if you are doing the contraction of the pairwise spinor-helicity variables differently than in the naive way. Now, it's a little bit problematic from the sense that now each of these terms, while the total amplitude is j equals 0, each of these terms pair by pair is not a j equals 0 amplitude. So it's, the jury is still out. Is this really a solution of Callan's problem or not? It's not completely clear. So some people tell us they will only consider amplitudes where pair by pair, you are going to get a j equals 0 state. For us, we are saying that, okay, so we have an amplitude satisfies all the conservation laws that you think you should, and it's a total j equals 0 state. But it's not j equals 0 for each of the pairs. Okay? So that's something, again, we can't decide without knowing the dynamics. And so maybe, this is the right resolution, maybe not. So that's something that that we're still working on.
Sorry, that was scattering of one
positron on a monopole.
On a monopole.
Yeah, so that one is the state that didn't have any known final states in the four-dimensional theory.
No final state is a two-particle state?
No, it's a monopole plus 3 particles.
Oh.
Yes, and but so the people knew that state could satisfy all the quantum number conservations. Yes. But it looked like that amplitude has to be vanished. Yes, and what we are saying is it's because they were always assuming that the particle is sort of I mean they were assuming that each particle is forming a J equals zero state with the monopole itself. So you have the 3 final state particles, and each pair is J equals 0. So if you require that, then we cannot write down an amplitude. What we are saying is that there's another way of writing down an amplitude out of the same particles, where the total J for the 3 particle plus the monopole system is 0, but it's not 0 pair by pair.
I didn't understand the motivation for the requirement that it be 0 pair.
Oh, it's because the claim is that otherwise it doesn't reach the core of the monopole. So because there's a centrifugal barrier, and in that case, they are not going to reach the core of the monopole.
So it won't happen.
It just won't happen. Yeah. So then the question is, when you have these complicated systems, how is the centrifugal barrier really? Is it given by the pairs, or is it just the total J? So again, that's something that we don't know, and some people like David Tong, said he doesn't think this is the right one. So I think our statement is very clear. This is an amplitude that is non-zero and its total J equals 0. If there are other conditions that it has to satisfy, like each of them has to be pair by pair 0, then this one will not satisfy. So again, the jury is out here. Okay, again, so is this the right dynamics? Is an open question. So maybe I should stop here because I'm running out of time, and if I can stay, let people out, and I can say a few words about what the dynamics is, if anybody is interested in later on. Is that okay?
Yeah, that sounds good.
Okay, let's do it like that. So let me just put up the conclusions. Oops. Here, yes. So I introduced this pairwise little group, yes, and that is telling you that multi-particle states don't necessarily have to transform as a direct product of the individual states, but there could be sort of a relative phase that is telling you how the 2-particle state transforms with respect to each of the 1-particle states. So that's what the pairwise helicity and the pairwise little group is. And this is actually a key ingredient for trying to write down the scattering amplitude for magnetically charged objects. Introduced the implementation of this pairwise little group in terms of the pairwise spinor-helicity variables to really get our hands on it and try to actually write down scattering amplitudes for monopoles. For the 3-point S matrices, we can actually do that very easily. And that one will be completely fixed. For the 2-to-2 scattering, we can fix the angular dependence via these monopole spherical harmonics. They pop out naturally out of our formalism. For the lowest angular momentum state scattering in the partial wave decomposition, we find that there has to be a helicity flip. We were able to sort of reproduce again the Callan-Rubakov effect and possibly give a resolution of the semiton puzzle. And then again, this is the part that I didn't get to, but I'm just telling you just the one line upshot is that until now it was all group theory, but the question is, what's the dynamics that is giving rise to this pairwise helicity? And again, what I'm claiming is that it is actually, the effect of a cloud of very soft photons that is going to be sort of surrounding these states, and it's addressing of the usual asymptotic states by this cloud of soft photons that is going to give rise to the pairwise helicity. All right, let me stop here.
And we don't have about the talk. Are there any questions?
Yes.
If you were doing 3-particle scattering, you could still imagine that there is a kind of interesting angular momentum that, let's say. Is there some way of quantifying your, 3 to 3, let's say?
So 3 to 3. Again, in principle, we have all the rules, yes. So we know what the building blocks are, but how to systematize it, yes.
You would do it 2 particles at a time. I was worrying about your comment.
So in the 2 to 2, you are worrying about the semiton comment, yes? So you see here, we didn't try to factorize it into 2 to 2. We just wrote down an amplitude. Okay, so this is the part corresponding to the incoming state, and this is the part that is corresponding to the outgoing state, yes? And here again, that is exactly what we did not do. We did not try to do it sort of, one particle with the monopole, and that you see what is happening here is that the ordinary spinor of the second particle is contracted with the pairwise spinor of the third particle. Yes. So that's what makes it non-zero. If you contract it with their own pairwise helicity variables, then it would be 0. So then the question is, and yeah, so I don't have a good answer to that. Is this allowed or not? Is this
Actually, that wasn't my question. My question was this: early on, you said that you didn't have a symmetry group when you had a 3-particle mission.
all right?
There was nothing there.
Yeah. But okay, so sorry. So that was not quite the right way of interpreting it. Yes, when I have 3 particles, the pairwise helicity for each pair is still there. Okay, so that was the part I didn't discuss in great detail. Yes, but again, we have written a whole paper on that. It's a little boring. That's why because it's very simple actually.
But why is that the right way? I would have thought that the angular momentum is contained in the 3-particle state rather than in sums of 2 pairs. So I would have thought that you should have something associated with the 3-particle state itself.
No. So that, yeah, no. So it's just the sum of the 2-particle angular momenta. So you have to pick a pair for each of them. Yes.
I see. Because you say that the angular momentum is a quadratic expression.
Right.
E cross B.
Exactly.
And so 1 and 0.
Exactly.
Okay, right.
Any further questions? So I actually had one.
Yes, go ahead.
So this non-factorization that you mentioned, should I think of that as coming from the constraints of the gauge theory, the fact that there is a gauge theory in the game and that's giving rise to constraints which leads to non-factorization in the dynamics, or is there something?
No, I mean, it's related to gauge theories. It's related to the fact that, again, because you're talking about massless fields, yes, they don't follow fast enough. So when we discuss the dynamics, essentially, what we find is that you have to modify, how you do perturbation theory, yes? Because when you do the usual interaction picture, yes, you're always assuming that the interaction falls fast enough, such that asymptotically you just have the 3-particle space. Yeah? So that's what is violated here. And then so there is a prescription called the Fayet-Coolidge method, which tells you how to deal with that. And again, this was not developed for this; it was developed for dealing with IR divergences in QED, ordinary QED. So that was and so this kind of effect is there already in ordinary QED, but the consequence of that is that the non-dropping off fast enough is that there are IR divergences. If you want to get rid of IR divergences, you have to redefine your external states. They will be the states that are dressed with the soft photons. And then what we showed is that I take exactly the same thing, and now I dress our charge and magnetic monopole states with our soft photons. Then their Lorenz transformation, because of the sea of photons, is going to pick up the addition. So that's where the additional phase is coming. It's sort of the collective effect of the soft photons that are surrounding your ordinary sort of bare states.
So I missed. I think I missed the basics.
Okay.
So you have a 2-particle state.
Yes.
You have the Hilbert states for 2-particle.
Right.
And you're looking at the Lorenz group, the Poincare group acting in this.
Right.
Okay. why does it pick up the charge at all?
It doesn't have to, yeah. So what, again, what the group theory told you is that it could, yes, that there is an additional quantum number. So when you have two particles, yes, you have a choice for picking an additional quantum number. That was the main point from the group theory, that, there's an additional symmetry there, it could pick up an additional quantum number. You don't have to, yes? The group theory doesn't tell you at all what that charge is. The group theory just tells you, when I look at this, two particle state, I should specify a Q. It could be as well zero, yes? It could be zero or could be non-zero. Group theory doesn't know. Now I'm saying, okay, so now let me take this I choose, yes? And then I'm asking what should be the choice, yes? Most of the time, indeed, should just be zero. Yes, but there's one special case where I know, or it's suggestive the fact that this new quantum number corresponds to an additional angular momentum in the system that is not contained in each of those particles. Yes, it's suggestive to identify that with the product of the electric and the magnetic charge. So, but I prescribe that. As the group theory does not prescribe that for you. Yes, Rick.
Yeah, so I mean, is it possible not in ordinary QED, but just like normal electrons and photons, you are saying this additional phases still exist for pairwise? Is it possible that these are relevant in some theory of?
So for ordinary, if it's just electrons, yes, then because there is no additional angular momentum, you would choose this phase to be zero. So again, it's E times G. So if both of them just carry E, then the G is zero, yes. So you need these two types of charges, this sort of mutually non-local charges present in order for this phase to actually show up.
Okay, if there are no further questions, let's.
Didn't have to do questions.
Sorry, there's actually a class.
Yeah, okay, so we should get out quickly.
There's T on the side. There's T on the side.
Yeah, I should just
Yeah.
quickly.
Yeah. Thank you for the one.
Yeah, thank you.